Buenas tardes a todos. Es un placer estar aquí en representación de la doctora Aida Rodríguez Roy, rectora de la Universidad de Puerto Rico en Humacao, quien debido a una situación propia de su cargo se excusa. Le extendemos la más cordial bienvenida a esta conferencia magistral en la cual el doctor Barish compartirá sus experiencias como científico de primera generación y cómo su determinación y creatividad lo llevó a ser reconocido en el 2017 con el Premio Nobel de Física, reconocimiento que comparte junto al Dr. Rainer Weiss y el Dr. Kip Thorne. En el 2015, estos investigadores lograron la primera observación de ondas gravitacionales, una predicción de la teoría general de la relatividad de Albert Einstein de hace más de 100 años. En nuestra institución, estamos honrados de contar con la participación del Dr. Barish, el cuarto premio Nobel que se dirige a nuestra comunidad. Nos llena de satisfacción saber que personas de distintas partes del mundo estén conectadas y que puedan disfrutar de esta actividad, que es parte de nuestro compromiso en promover la educación. Confío que esta actividad logre motivar e impulsar a las próximas generaciones a estudiar, a establecer metas y a trabajar por lograrlas. Agradecemos al Dr. Barish, a los panelistas Andy López Oquendo, egresado de la UPR, a la doctora Mayra Lebrón Santos, catedrática de Ciencias Físicas en la UPR Recinto de Río Piedras, y al profesor jubilado de Física y Electrónica de la UPR, el doctor William Brookman San Miguel, por su tiempo y compromiso en promover espacios de aprendizaje y de intercambio de conocimiento. De igual forma, agradecemos a la doctora Idalia Ramos Colón, del programa Premio, así como a la doctora Lilian Casillas y al doctor Kevin Alicia Torres, del programa Proud, por auspiciar esta actividad.
Okay, muchas gracias, Héctor. Voy a cambiar aquí a inglés para presentar a nuestro speaker del día de hoy. So Dr. Barry Barish, he was born in Omaha, Nebraska. His parents came from they were Jewish immigrants that moved to Nebraska. Then after his spending his early childhood in Nebraska, he moved to LA in California. He described himself as a quiet child, but a very good student from young age. He actually went to public school through high school. By the time he entered high school, he was interested in sport. I was actually, I'm trying to learn tennis. I was very surprised when I learned that he really enjoyed playing tennis, and he actually won some honors playing tennis as well. So hopefully he gets the chance to come to Puerto Rico. I will make sure that we can make some time to play some tennis. That's something that I'm trying to learn. Although he was always at the top or near top of his class, he didn't have a real direction, right? As a first generation, being the first one to earn a degree from his family, this resonates a lot with me because I didn't have that real direction throughout my career. He didn't have, his family didn't have general expectation. Actually, they wanted for him to become either a doctor or a lawyer. But he was not very interested in any of these degrees, although his brother became a lawyer. He said that he lacked much good guidance, but he decided to study engineering based on the fact that he was very good at math and he liked what he knew about engineering. He entered the University of California, Berkeley, to pursue his doctoral degree, and right after obtaining his PhD, he landed a postdoctoral job at the California Institute of Technology, or CARTech, which has been his professional home ever since. Dr. Barish is a role model for many of us. As a first-generation scientist, for me, it's very inspiring and empowering to know someone with similar background that has achieved so much throughout his life, especially obtaining the Nobel Prize. In Puerto Rico, across many universities, 25 to 40% are first-generation students. And for me, I never realized that as a first-generation student, obtaining many awards, you could also obtain a Nobel Prize. And for me, that was shocking and surprising, and I'm really pleased and honored to host Dr. Barish here in Puerto Rico, although it's virtually. we hope that he can join us in the future in person. With that said, and with no further ado, we introduce you, Dr. Barry Barish, Nobel Prize in Physics 2017. Thank you so much, Dr. Barish, for joining us. The virtual stage is all yours.
Thanks for the very, very kind introduction. I'm proud of the fact that I'm a first generation achiever, if you want, and I still have returned to my high school days. I returned to my high school for graduation to honor the fact that I came from that school sometime in the past. Anyway, today I want to talk to you about some outstanding science, really. Part of it being what we discovered for the Nobel Prize, but I'm going to cover this subject for this audience a lot more broadly. So I'm going to first tell you some history, which some of you may know parts of, but probably not all of it. And then I'll end up with telling you what Einstein did to make a new theory of gravity. And then I'll talk about the long haul and what it took to detect gravitational waves, what I won the Nobel Prize for. Then I'll show you some data so you can see that, and some of the newer science that has happened, which is pretty amazing since we made the discovery only 5 or 6 years ago. And finally, I'll talk a little bit about the future. Hopefully I can pack that all in 1 hour. So let's start with some history. So first, I think all of us learned something in school about gravity from Sir Isaac Newton. In fact, Sir Isaac Newton wrote down his theory of gravity in 1687 in a very famous book where there's maybe 100 copies of it in the world now, called the Principia. And in the Principia, he wrote down first the scientific method, which we don't do it the way he says, but basically the idea of how you learn truth through the scientific method is basically the same spirit as Newton that we do today. We may use statistics and other ways to validate, but that didn't exist in his day, but he has that. The rest of the volume, which is 90% of it, is his life's work and writing down his, what he called unified gravity, universal gravity. And that meant universal meant that he gave a theory of gravity, or an explanation of gravity that worked everywhere. It didn't matter to him whether you talked about the apple falling out of the tree, or the moon going around the earth around the sun, or things like the tides that we have in the ocean. So this universal gravity he presented with a rather simple formula, which I give here. You have two masses, and the force of attraction between them is proportional to how massive each of them is, the product of the two masses, and inversely proportional to the square of how far apart they are. And the strength of it, this little formula, is capital G. He didn't know what that was, how strong gravity was. And it took another 100 years, actually, for someone to show what the strength was of gravity. But this formula in this theory of gravity, which he wrote down, is probably the most successful theory of physics of all time. It existed basically describing everything to do with gravity for more than 200 years. And yet in 230 years or so, Einstein created a new theory of gravity, which I'll talk about. That didn't mean that Newton's theory was wrong. It meant that Newton's theory wasn't complete and wasn't able to describe everything about gravity. In particular, I think the motivation was that Einstein talked about the theory of relativity, which you've all heard of, and masses moving at near the speed of light. That changes the idea, and Einstein created the theory of special relativity, and he presented that in 1905. Then he decided, after he presented the famous E = mc squared, to concentrate on how to put acceleration into the same theory, the theory of relativity. And it took him 10 years. And in 1915, he came out with a theory that had not just velocity, but accelerations. It's a rather complicated theory. By putting in accelerations, it's a theory of gravity. The theory of gravity is similar to Newton's in all the areas that you're used to doing, but there are some key differences, which I'll talk about. And so I write down the formula here, and I won't talk about this complicated formula today, but just to be as symmetrical with what I did for Newton. The key to it, which I won't go through in detail, but I'll give you a sense, is that he unified space and time. We've all heard that, but everything in Einstein's theory is a four-dimensional calculation. We all know X, Y, Z space, but if you integrate time into it, it's rather complicated. It took him 10 years to develop that. And then we have a four-dimensional combination of space-time. It's one word. You put it into Microsoft Word. They don't know that yet. They put a little wavy line under it. But basically, space and time are all integrated together. We won't go through Einstein's theory in detail, but I'll point out a couple of things. First, and by the time Einstein came along, there was essentially no problems in physics that anyone had seen that violated the little theory that I already showed you of Newton's, except one, which I'll talk about in a second. But let me say in words. The first, it described everything about motion of planets and all that. The first time there looked like there was a discrepancy was in the maybe 1820s or 1830s. And at that time, the orbit of the planet Uranus didn't seem to completely obey Newton's theory of gravity. And that was a complication. You could either say the theory is wrong or something else was wrong. And there was a famous astronomer at that time, a Frenchman, who basically said the reason it's not obeying it must be because there's a planet that we don't know about. And so he basically reverse engineered the problem and said what had to be missing to obey Newton's theory. And that he came up with what the planet would be, decided that one should look for it. He was in Paris. He sent a letter to an astronomer that he trusted in Berlin. The astronomer told the astronomer where to look in the sky that night or following nights. And within 1 degree, the astronomer saw a new planet. That was the planet Neptune. And that's the history of the discovery of Neptune. So then Newton's theory was still perfect and okay. A little later, there was a second discrepancy, much smaller, that was discovered for the planet Mercury. There's a planet Mercury, which I show here, has a very elliptical long orbit going around the sun. And each time it goes around, because of the positions of all the planets and the sun itself, it comes back to a somewhat different place. And you can calculate how far it's moved or what the angle is using Newton's theory. And you can measure it, of course, by what the real effect is. And it turns out that Newton's theory was wrong by about 10%. So it was almost right, but wrong by about 10%. That stimulated in the late 1880s a whole bunch of searches for missing planets or objects between Mercury and the sun. There were some discoveries, but they proved to be false. And so by the time Einstein came, this discrepancy was still there, even though it was not the motivation for Einstein. It was one difference, which we still didn't know whether there were objects that hadn't been yet seen. And in fact, after Einstein's theory, NASA did an extensive search for objects between Mercury and the sun, and they didn't find anything larger than about 10 kilometers in size. So anyway, Einstein then created his theory independently, putting accelerations in. And you all heard the words that it amounts to first space and time being together, but words like warpage of space-time. So what does it mean, a warpage of space-time? I illustrated here in a picture that looks a little like a trampoline. If I have a trampoline and I put a big mass on it, it'll sink in the middle and the trampoline will no longer be flat. So if you think of the coordinate system here, the Earth is shown there. And that if I don't have this distortion that's created, the moon, which is outside the Earth, wouldn't roll toward the Earth or pull. So the force to pull the moon toward the Earth is actually a distortion of space-time, illustrated like this picture, although in Einstein's theory, it's more complicated. Every point on this grid is both a point in space and a point in time. It gets altered, so it becomes a very complicated technically to calculate the details in Einstein's theory of general relativity. Einstein put this forward in 1915, and of course, the first success was that it got the right answer for Mercury around the sun. So basically the 10% discrepancy that Newton had after 200 and some years, the new theory got right. That's hardly enough stimulus to make people believe general relativity as a new theory of gravity after all the success of Einstein's theory. But so Einstein predicted something new. And that is, if I have a distortion of space and time, like shown in the left in my picture here, the big distortion is for the sun. The smaller one, the little dimple, is the Earth, and that describes how the Earth goes around the sun. But because the distortion of space-time is there near the sun, it really doesn't matter whether the object going near it has any mass or not. We think of Newton's theory that it's the mass of something that attracts them. So Einstein made the prediction that if he has light that has no mass, but light is aimed and grazes near the sun, it'll go through an area which is distorted and it'll bend. So Einstein predicted that light would bend, and he calculated exactly how much if light were going near the sun. And then he proposed that the way to test that was to look at a full eclipse of the sun, just as stars are going behind it because they're moving, and measure whether that light that comes from the star, as I show on the right, goes behind it, gets bent. And that experiment was done by Sir Arthur Eddington in 1919. And he got exactly the predictions of Einstein, which is what made Einstein famous in the world. He basically predicted this bending of light, which captured the imagination of the public, and of course gave general relativity some relevance to all of us, even though Newton's theory of gravity describes almost anything we would want. There were some flaws in Newton's theory. He even realized one of them himself. He realized that there's something inconsistent about the fact that when the apple falls out of the tree and you see it right away, that there isn't some time for the message to get, in his theory, from the apple falling to you. Well, it isn't very important for the apple, of course, but imagine the sun and the Earth. If the sun were to disappear right now, we wouldn't know it for 8 minutes, because that's how long it takes the message, in this case light, to come from the sun to us. So it takes 8 minutes for it to travel to us. Similarly, gravity, if something happens, has to take some time to come to us. And in Einstein's theory, gravity and light travel at exactly the same speed. I might have, if I think of it, show you the evidence that from our experiment, that not only do they travel at the same speed closely, but to 1 part in 10 to the 15. Anyway, this is new. Einstein's theory, gravity moves at the speed of light. So that's an improvement or a difference with Newton's theory. And Einstein, at the same time, made the prediction of the bending of light, which I showed. An interesting thing is when we make discoveries in physics or in astronomy, it often leads to that discovery being useful for other things. This bending of light has turned out to be a tool that's used in modern astronomy called gravitational lensing, which I show in this picture here, where you can study one object by using the other source and the fact that the images are focused. This is an example of a darkened object where the sun, where the image goes around it. Or the most famous one is called the Einstein cross, which you can see on a very clear night if the conditions are just right, almost with the naked eye, or some people claim to see it with the naked eye. Those dots are basically this light coming around and bending, as I said. One more thing before I get into gravitational waves is that we often think something as abstract as Einstein's theory of general relativity or theory of gravity has no use. In fact, it does. GPS, which we all use almost every day to drive around in our car or to walk on a hike or whatever we do, relies on a set of 24 satellites that are going around the Earth at about 14,000 kilometers an hour. And when they move around the Earth at that speed, we know from special relativity that clocks that are going that fast go more slowly. That's the theory that you learn in physics of special relativity and that Einstein put forward in 1905. That correction, which is not controversial, was made in the initial satellites so that when they calculate where you are, it takes into account the 7 microseconds. But there's a second correction that's necessary, and that correction is for general relativity, this new theory of Einstein's. And it's due to the fact that the satellites are high in the sky, and the gravity at that point is only about a quarter of what it is on the Earth. And so if you do the correction for the fact that the satellites are moving in a smaller field of gravity, there's a correction for general relativity, which is the opposite sign. It says that clocks move more faster, and that's a 45 microsecond per day correction. Well, microseconds don't mean anything. Well, let me translate that. Basically, the total correction, which is made in the satellites to tell us where we are, wouldn't work at the level that if you take a road, a typical road, and you drove down it and you did not make the correction for general relativity, how long would you stay on the road? If I did that calculation, which I don't have time to do for you, it's pretty simple. It takes about 2 minutes. So basically, the fact that we use GPS to run us around roads and so forth wouldn't be accurate enough to do what we do without general relativity. So general relativity, that's Einstein's theory. That he put forward in 1915. Now, as a scientist, it's mostly very important for what we call relativistic astrophysics. That is for studying the universe where objects are going very far away or going very fast. We have to use general relativity, and that's the main place it's used in science. Of course, it's used in GPS, as I said, but in terms of scientifically. In 1916, 1 year after Einstein published his famous theory, new theory of gravity, general relativity, he published a little paper. It's the beginning of it is said here. He was a sole author. It's only 5 or 6 pages long. It's not a very good paper. In terms, it's not very quantitative, but it's in that paper that he postulated the existence of gravitational waves in 1916. In the paper has some errors in it. In fact, the errors are serious enough that it would have made us make false conclusions if that was the theory that we believed in the discovery we made. But in the paper, he doesn't derive from general relativity that there are gravitational waves. Instead, what he did is notice that the formulas of general relativity, if you put them together in a particular way, look very similar, maybe different letters, but look very similar to the equations of electricity and magnetism. But electricity and magnetism has built into it electromagnetic waves we all use every day, light, that's how we see each other, radio waves, microwaves, light, ultraviolet, infrared, all of that is electromagnetic waves. He predicted just by not deriving it, but by a similarity that he noticed in the equations, that there must be gravitational waves. the paper has an error that had to be fixed. He wrote a second paper in 1918. He fixed that error. He never admitted he made an error, but he did it right in the second paper. And the second paper tells us what kind of movement of masses will create gravitational waves. And that's what we call a quadrupole formula. Quadrupole means four, or the motion has to have a part of it that is got four pieces or four parts, or to the fourth power. In electromagnetism, it's square. And so what that means, and physically, instead of these murky words, is that if you have two charges in electricity and you put them near each other a little bit, like if you can see me, they go up and down. That's what Hertz did in the 1880s to create electromagnetic waves. He went in the next room and detected them, moved forward and backwards, and saw that they were wave-like. And that was the discovery of electromagnetic waves. The same idea for gravitational waves, only the formula to produce them requires a quadrupole. I'll show you what that means, translates to in just a minute. So that translation kind of is shown in the illustration here. If I have two masses, in this case I've drawn equal ones, but like the sun and the earth, or the earth and the moon going around each other, then as they go around each other, they create what's called a quadrupole moment. If they're going fast enough and the amount of energy is enough, they radiate away, as shown kind of in this cartoon, energy in the form of, in Einstein's theory, in the form of gravitational waves. And they'll go, by what I said before, at the speed of light. And this is basically the qualitative picture of gravitational waves. What goes out is energy and distortions of space and time. Nothing you can kind of pick up. There's nothing like the photon in electromagnetism. They're just distortions in space-time. A little bit like when you throw a stone into a still pond, the stone sinks to the bottom. That's like the center of this. And the ripples that go out are just in the water itself. There's no objects or anything in there. That's similar to the idea here. But of course, this is going out at the speed of light. So that's the idea. And the detailed formula for it, I show here. I'm not going to derive that. I give the information on the left for anybody who happens to know enough in the audience of how I got it. But the reason I put this equation up is for those that know electricity and magnetism, it's different letters, but it's the same equation as we have for making electromagnetic waves, plane waves. And so in electricity and magnetism, we have a plane wave, what we call a plane wave, that propagates through space, has two components, the electric and magnetic component. They're at 90 degrees to each other, and they go at the speed of light. In this case, we'll have two waves, just like in electromagnetism. They're actually at 45 degrees to each other, which is a technicality from quantum mechanics. The gravity is what we call spin 2, but they also propagate in Einstein's theory at the speed of light. So that's what we're going to try to do today. So Einstein came out and wrote these two papers, 1916 and 1918. Most of the physics community during those years was discovering quantum mechanics. So this didn't make a lot of, didn't get a lot of attention. And there was really no other papers written about it. By the 1930s, Einstein returned to this problem with his associate, Nathan Rosen. By that time, he had immigrated from Berlin because of the Nazis to Princeton University. And he tried to do what he hadn't done in 1916 and 1918. He tried to derive gravitational waves from the theory. And he failed. And he failed because he got what we call infinities in the calculations. That turns out to be something that's very common when you're a student and you learn general relativity, because of the fact that you've made a four-dimensional space, and it's hard to do that consistently. That is X, Y, Z, and time. And so there's what we call coordinate singularities that students get often. Well, Einstein got that too. He didn't realize it. So he wrote a paper questioning whether gravitational waves actually exist because he got these infinities. And it was seen by a referee where he made a mistake, but he basically then rewrote the paper, submitted it somewhere else, never wrote anything else in his lifetime on gravitational waves, and they certainly were not believed by the broader community or looked for before he died in the early 1950s. So in 1957, soon after Einstein died, there was a conference in Chapel Hill, North Carolina, which is where most people believe that the community for the first time believed that gravitational waves must exist. And there was a very nice derivation, theoretically, from general relativity by a theorist named Pirani. I have his name at the bottom of this. He was a British theorist. And then also Richard Feynman, famous physicist from my institution, Caltech, was at this meeting. And he said, well, if gravitational waves exist, they have to be able to do something. And so he made what we call a Gedanken experiment, that is a thought experiment. And the thought experiment was if you have a rod and you put two rings around it and a gravitational wave comes through, the gravitational wave has the features of distorting the space. By distorting the space, it basically puts some force on the two rings. They move out, maybe back and forth. But what does it mean to do that? It means that it created some friction between the rod and the rings. And that friction is a transfer of energy, heat. So it basically is a demonstration that energy can be transferred. And so after that meeting, basically people believe there should be gravitational waves. And the theory theoretically was developed, but more importantly, the experimental search for gravitational waves began in the 1960s. And so how do we detect gravitational waves? So let me talk about that. If we have these two objects that are circling each other, I show them in the left, they may be spinning, which is what I have in this picture. They themselves, like the Earth is spinning on its own axis, not just going around the sun. And they eventually, time goes to the right. So they're spinning, they radiate away energy like the cartoon I showed earlier. They merge together and then they somehow settle down. And so we expect to see something which I've drawn very schematically on the left. The first part of it, where it says known on the bottom, is the part I can calculate from general relativity. When they actually come together, that's new physics of what happens in black holes or whatever, neutron stars, or whatever the objects are. And at the end, it has to settle down. And that, again, we can try to calculate or understand. On the right, I show a picture of basically what the signals will look like. You get them merging together, going faster and faster, and making a bigger and bigger signal as they come closer together. So you see these up and down become narrower and bigger, and then they merge together. The one on the top is for a smaller mass, and the one on the bottom, a larger one, which will have fewer cycles at high frequency where we test things in our lab. So that's the idea. What happens? This is how you now can detect gravitational waves. The little picture on the right is a ring of free masses. It has a radius L in my picture. And the amplitude of the wave that we actually measured is incredibly small. That's why it took so long, 10 to the minus 21. That's the same little h that was in my formula back earlier. And the change in distance, how much this won't be a perfect circle by these masses being free to move, is delta L, the change in length, will be this 10 to the minus 21 times L. That's a very small number. And because it's so small, we actually make our apparatus a ring kilometers instead of meters. And so the effect on the bottom, which I say is 10 to the minus 21, becomes about 10 to the minus 18. That's still smaller than the radius of a proton. So we have to see a difference, distortion that's smaller than the radius of a proton. And that's why the experiment is so hard to do. The first attempt looks a little like Feynman's experiment. This is a big bar of aluminum. The experimenter is named Joseph Weber, and he put detectors around it. And if a gravitational wave goes through, he expected to see the distortions of recorded in these little piezoelectric detectors. The idea was a very nice one. Unfortunately, he wasn't a very good experimenter, and he claimed false discoveries which didn't stand up to the scrutiny of other people's measurements. But this began the field of experimentally trying to detect gravitational waves. This technique was used for another 30 years, improving it, making it cool, and cryogenics and so forth. I started to become, I didn't like this technique personally because it's most sensitive at the frequency the bar likes. That is, if you hit this bar with a hammer, it'll ring typically maybe at 1,000 times a second, 1,000 hertz. But there's nothing that tells you that gravitational wave is going to happen to pick that frequency. So you really would like to have a detector that can look at a broad band of frequencies. And that's the interferometer technique that we used. And it was when this technique was starting to be discussed that I became interested in this problem because it could be broadband. So what happens here is an interferometer. I've got a picture of it. I'm not going to go through any other details. We use a laser beam, comes in. The beam is split in two directions in a beam splitter. So it goes to the right, goes to the left, 90 degrees to each other. And if nothing goes through and the length of the arms is exactly the same, which we calibrated and make it, the light will come back, you invert one compared to the other, and they just cancel each other. And in my little thing that says light detector, you see nothing. But if one of the arms becomes slightly longer or shorter than the other, it'll take a different length of time for the light to go down one arm than the other arm, and some light then will come and be detected in the detector at the end. So what happens physically when a gravitational wave goes through as a function of time is shown at the bottom. It becomes longer in one direction, then longer in the other direction, and it goes back and forth at whatever the frequency is of the gravitational waves. That's the technique that we use. We have to do it very, very accurately. These are the two detectors that we built. You can see they're kilometers in size. This one on the left is in the state of Washington. Where they are was picked by the US government, Congress, not by us. It's sitting on a Department of Energy reservation. It's high desert, as you can notice. And the one on the right is in Livingston, Louisiana, and that's in a commercial pine forest where they cut down the trees to make paper and wood. And although they look very different, it turns out that the instruments are identical, and we work very hard to keep them identical. I'll show you why we have two instruments in just a minute. So we have two of these. I'm not going to show you any details except to show you the size. Basically, a man goes up to these lower ports about halfway. So it's about 15 to 20 feet high and has many ports all around it, you can see. And then the long arms go out to the left and to the right. Those ports are there so that we can change and make more sophisticated or change the mirrors or do anything. It's a living laboratory where we become better and better at detecting gravitational waves. The two detectors, as I showed in the picture, were put, one in Livingston, Louisiana, and one in Hanford, Washington. Those are 3,000 kilometers apart. At the speed of light, it takes 10 milliseconds to go from one to the other. So we require that no matter where a gravitational wave came through, if it came through from the lower right through Livingston and then went to Hanford, it would give a signal in Livingston 10 milliseconds before Hanford. If it came down from the left, it could be 10 milliseconds earlier in Hanford than Livingston. And anywhere in between, it's going to be closer in time. So we require that we see a signal in both detectors within 10 milliseconds. This is for two reasons. One is to give us confidence that we see gravitational waves and not something else, because anything on the Earth travels at the speed of sound, not the speed of light, and won't make both detectors go in that close proximity. So that we use two. Also, using 2 and in fact 3, which I'll show you, gives you an ability to point to where in the sky the signal came from. This is what the sensitivity looks like as a function of the frequency. So I told you that a bar has a given frequency, you bang it and it rings. You're used to a bell ringing, it rings at some particular frequency. Gravitational wave interferometer goes from tens of hertz, the shaded region is where we're sensitive, from tens of hertz to 10,000 hertz in the region that's shaded. We're limited by what and how sensitive we are by 3 things. On the left, where it says seismic, we're limited by the earth shaking. We're on the earth, and we have to prevent the earth shaking from changing the distance of the arms. On the right, it says shock. That's a technical term for the fact that we need to make the measurement many, many, many times, and we need a lot of light. The more light you have, the lower that is. And in the middle, there's a line that says suspension thermal. And that means that we're working at room temperature and that the atoms move around in the detectors that we have. So the sensitive region is there. And if you look over to the left, the scale is the 10 to the minus 21 that I talked about. And the frequency band, interestingly, goes from tens of hertz to 10,000 hertz. That should be familiar to you. That's the audio band. So we use exactly the same frequencies as our ears. And that just tells us that our ears through evolution have learned where we can communicate with each other where things are quiet enough on the earth. So our ears respond to tens of hertz to thousands of hertz. And likewise, the earth is quiet. If we want an instrument, we have nothing to do with audio, but in the same frequency band. So we do these studies in the so-called audio band. I'll show you how to study other frequencies at the very end. This is that same curve as a function of time in an apparatus as you make it better and better. The different colors are kind of each half a year apart or so, where we run, we get a certain sensitivity, learn what limited us, run again and again and again until we basically got down to our design. The challenge to actually make the detections is shown here in 2 numbers, and they're very tiny numbers. In order to make the detections at the level of this 10 to the minus 21, which is the size of the signal that we detected from these black holes, which I'll show in a minute, we need to be able to tell the difference in length of the 2 arms to 1 part in 10 to the 12. Some of you probably have seen interferometers in, say, a laboratory or commercially somewhere where it's used. And those, in the physics laboratory, they're probably good to, you see what are called fringes, and you can tell those to maybe 1 part in 10 or 1 part in 100. Commercial ones, the best commercial ones, maybe 1 part in 1,000 or 1 part in 10,000. We have to do it in 1 billionth of 1 billion, one part in 10 to the 12. That's the wavelength of the light. That took years of innovation, which I don't have time to go through, of how to do interferometry at this spectacularly precise level. The second problem is, how do you get rid of the vibrations of the earth enough so you don't shake the apparatus? That again has to be done to 1 part in 10 to the 12. And as I'll mention in a minute, was the key to us making the final detections. Being able to do that is very hard. This is interferometry starting from just a simple picture I drew, and I'm not going to go through it, I don't have time, to a very complicated one where we put in all the innovations necessary to get the factor of 10 to the 12. And this is the problem of isolating from the earth. It's easy to understand, but hard to implement. So we're all familiar with how to get rid of the shaking of the earth or a bounce. We do it in our cars. So our cars have shock absorbers. Without a shock absorber, like the very early cars, if you go over a bump, you feel it as a big bump. But now when we go over most bumps, we just feel it as a little smooth effect. That's done by under the car having shock absorbers. They can't get rid of the energy, but they absorb the energy of a high frequency shock, and they move it to very low frequencies where you basically don't feel it. We do the same thing. We basically made the world's fanciest shock absorbers. And then we made 4 layers of them. And those 4 layers were to isolate us from the Earth. That was what we did for more than a decade, and it wasn't good enough to detect gravitational waves. So lastly, the big single advance that enabled us to detect gravitational waves was to add to this stack of 4 layers of shock absorbers active isolation. So what do I mean by active isolation? Active means that we actually sense the movement and push back against it. So we buried inside of this an array of seismometers, and each seismometer would measure how much motion was left beyond the shock absorbers. And then we had little actuators that pushed against whatever was measured. And that brought us to the 10 to the 12, and we detected gravitational waves. So I showed that. This is then the first detection of gravitational waves. What's shown on the left is the scale 10 to the minus 21. So just the scale that I said. On the right, going to the right is time, and that's 2/10 of 1 second. And you see the little wiggles. Those little wiggles come each time this is an object, 2 objects going around each other like I drew before. And each time they go around, they radiate some energy, and you see it in these wiggles. As they get closer together, the wiggles get higher and narrower, as you can kind of see. This was a surprisingly heavy object, and we only saw about 6 or 7 wiggles, which are shown here. The top graph picture is the interferometer in Washington. The middle one is the interferometer in Livingston, Louisiana. And to the eye, they look the same. If I put one on top of the other, in fact, and just slide it very slightly, because we have the plus or minus 10 milliseconds that I told you about, then they look almost identical to each other, as you can see. This data is almost unique in physics. We have done nothing to do a data analysis, to smooth it, to take away backgrounds. It's just the data that comes out of the apparatus. This is a second picture of the same thing, which is basically shows you how conclusive the result was immediately. On the upper left is the data from Washington, the upper right, the data from Livingston, Louisiana. In the middle, the frames in the middle, is Einstein's calculations of 2 objects going around each other that are about 30 times the mass of our sun, and they're merging together by general relativity. And you can see they look very much like, they're not as jagged because they don't have noise in them, but they're very much like the ones above. And in fact, if I subtract the middle from the top, I just get a residual, which is the noise in the system. That's how well we measured, with no pattern that's seen. So that's a very good check. And this is the graphs that we showed in the discovery paper of gravitational waves. From that, I'm just going to flash a formula. I'm not going to spend time on it. There's a detailed formula of what these waveforms look like. And from that, you can calculate all kinds of things. You can calculate how far away it is, how fast they're going, whether the objects are spinning, whether there's any precession, the location in the sky, and so forth and so on. In other words, there's a huge amount of information that exists in these waveforms that I showed you. And so from that, we were able to see what was happening for this very first observation is shown here. The primary black hole, 2 of them were just about 30 times. The symbol on the right is the mass of the sun. The little circle with the dot is the solar. So one is 36 times the mass of the sun. The second is 29 times the mass of the sun. And the final object that we measure is 62. Notice if I add 36 to 29, I get 65. And so that means the equivalent of 3 masses of our sun went away in the form of gravitational waves, or gravitational energy, in just that 2/10 of a second. At that moment, that was the most energetic object in the sky anywhere. Then we measured the other things, how far away it is. It's about 1,000 light years, million light years away, and the other technical parameters. We have the second measurement looks different, and that's because I'm just showing it to say each one is different because it's different masses, different places in the sky, and so forth. And so this has many, many wiggles. The reason is it's lighter, and so it basically goes to higher frequency and is seen in our apparatus up to high frequency. You can look in detail at the waveforms in these different areas and test it against Einstein's theory, and that we've done. And when we do that, we can see that there's no evidence that there's any carrier, like the photon is for electromagnetism, that there's any carrier, what people like to refer to as the graviton. So one part in 10 to the minus 23 in the units we measure EV over c squared. So basically it agrees with Einstein's equations beautifully. This is just to illustrate all the first ones we saw. Each one is quite different from each other. So getting a whole array of them, we can start to learn about what these objects are in the sky. And this is actually the first real observation of black holes in the sky. Otherwise, they were inferred. I want to show you at least one other thing before we leave. If we have not just the two LIGO detectors, but a third detector, then we're able to triangulate like on the sea and know where we are quite accurately. This picture on the right shows that with LIGO's two detectors, we can see where we are in the sky in these stripes. But then in the lower left on this picture of the Earth, we see the one that says GW 170814. We get much better accuracy with the third one. 2 years after we detected gravitational waves, a detector in Italy started to be sensitive to gravitational waves, not as sensitive as LIGO, but sensitive enough to be useful. And that gave us this ability. It was just at the right time because we never saw for any of the black holes up till today, where we have almost 100 of them, any report of anybody seeing anything in their telescopes, any kind of telescope, radio, anything, coming from that object. And there shouldn't be from a black hole. However, the object that we saw, other object that we saw, was not black hole, but what's called a neutron star. Instead of being for 2/10 of a second in our apparatus, neutron stars are very light. They're basically the final object when a star burns up all its fuel and collapses. And they go to thousands of oscillations in our apparatus. We detected the first neutron star, shown in this graph here on the left, as a big line that says merger at the very top. And 2/10 of a second later, 1.7 seconds later, actually, it was also observed, and this was the first case, in a satellite in high energy photons. That's the first time there was a signal from gravity and a signal electromagnetic at the same time. This immediately from our data, I can't go through the details, had the features from our data of being what's called a neutron star, not the black holes that we saw. Neutron stars do radiate. They have nuclear reactions, they give photons, they have signals that might even give exotic particles like neutrinos. But this object turns out to be 150 million light years away. And within less than 2 seconds, we see the same signal in light, electromagnetic radiation, and in gravity. And that means to 1 part in 10 to the 15th, they traveled at the same speed. The reason there's any difference in time, if there is because they come from different physics. The merger, when they're just coming together, gives you the gravitational wave signal, while after they merge, the nuclear physics gives the signal that was detected in the satellite. And that's something like a couple seconds later. Having seen that, we turned on all the detectors that look at electromagnetic radiation or even neutrinos in the world, pointed them in the sky at what we had seen, and more than 2,000 different instruments. That was done very quickly. And we were able to see exactly where this came from in the sky, what galaxy it came from. And I'm sorry to go fast. fast, but I'm running out of time. But in general, looking at this and measuring it through the different wavelengths, high energy photons, X-rays, finally radio waves that come 16 days later, it was seen by all of them. The amount of light or the amount of energy at each one was seen. And that fit very well a theory or phenomenology called a kilonova. A supernova is when a star collapses. This is called a kilonova. And interestingly, that has it's the last physics I have time to show today, but it has a interesting consequence, and that is that in a kilonova collision in the theory, it has a lot of nuclear physics that happens. We've had a puzzle in physics for decades. Physicists like to think they try to explain everything, whether we can or not. But the problem is simple. It's how, when the Earth was formed, did maybe our favorite elements like gold and platinum that we like to use in our rings get there? We know that most of the universe is made out of hydrogen and helium. Stars burn up their fuel and make their light and energy by the fusion process. And that works to make radiation up to iron, but nothing heavier than iron, or not very much heavier than iron. So to make heavy elements like gold and platinum, there has to be another mechanism. We, for years, have said that there was some exotic mechanism going on in the burning or collapse of a star that must be making this, because as physicists would try to explain it. It turns out that a kilonova explosion like this is a very nice way to make heavy elements. It's very much like what we do in the lab that made all the very heavy ones. If you look at the periodic table and you look at the heaviest elements, they were made by taking neutrons and bombarding a heavy element and then making a heavier one. They're not necessarily seen free in nature, but they're made in the lab and then somebody's named them. And those are the ones past iron, which is in the middle of this somewhere, how they've been made and through the years. But if we want to take then platinum and gold that are beyond iron, they probably were made by collisions like I just showed you. And we just observed, of course, not that one, but one that's made many, many years ago before the Earth was formed. And they made a lot of gold and platinum. In fact, if you look at the one we observed, it made a huge amount of gold itself. If we calculate it, the neutron star merger that we saw produced about 100, the equivalent of 100 Earth masses of gold. So mergers like this in the distant past probably are what made, on the one event, I say probably because we need more data to make it definite, but it looks like this is now the best explanation for how the heavy elements got into the Earth, which is an interesting statement about science. We're not studying Earth science at all, but when you learn things in one part of science, it often gives you understanding in another part. Let me just end with a couple of quick slides just to give you a sense of the future. We'll be much better in the future in terms of being able to point in the sky. The lower right here is how well we can point in the sky when we get more detectors working in the world. Right now, the upper left is how well we can see those little oblong things are the resolution. That's important for doing any sort of astronomy. This is the number of samples of gravitational waves that we've seen. We're out to where my pointer is about 700 days. We've seen just under 100, and we keep improving the detector. You can see that it gets steeper and steeper. And in the run next year, we expect to be up to several hundred examples. This is only less than 10 years after the discovery of gravitational waves, and we're already making science of it, which is wonderful. We're also designing what a next generation detector will look like. And it'll be probably bigger than LIGO and have some technical features, which I don't have time to go into, which will make it another factor of 10 or so better. We're not limited by anything fundamental. We're limited by how well we can make the technology at this point. Lastly, I show the fact that LIGO is shown in the far right here This is frequency. So LIGO looked at what I call the audio band. If we want to look at lower frequencies, we go into space. The thing called LISA here is going into space and doing interferometry. A little technically different, but like we've done. And then you can look at lower frequency. Yet lower frequency is being probed by something, by using information from pulsars, something that we do in astronomy. So eventually we'll cover all the frequency band, much like it's done in astronomy. In astronomy, it advanced for the first 300 years after Galileo by making better and better telescopes. But in the last 50 years, the huge advances in astronomy are because we look at the same phenomenon, but we look at it in different ways. We look at it in the radio, look at it in high energy gamma rays, we look at it in the visible. And all that together gives us information. The same will be true for gravitational wave. This is just a picture of what will be done in the sky. 3 satellites forming a triangle, 2.5 million kilometers apart. And that'll be and the signals go back and forth. If a gravitational wave goes through, it makes the timing different for the arms. This is just the pulsar rate that'll be seen. So my final comment is that astronomy as we know it began with Galileo in the early 1600s. He took advantage of the fact that high quality lenses were starting to be made for glasses for people's eyes. And he didn't invent the telescope, but he knew that with the higher quality lenses, he could make a telescope that had the features that he wanted. So he made a telescope, not the first, as I say, but nearly, using lenses that were using the technology that was for glasses. And he looked at Jupiter. When he looked at Jupiter, he saw that Jupiter had 4 moons. That was supposedly the 4 moons of Jupiter, which is what I learned. Now we know there's more than 4, but he saw the 4 moons of Jupiter. That was a landmark because it was the time at which we learned something about the sky and the universe beyond what we could see with our own eyes. And we're using an instrument. That was the beginning of astronomy. It's been 400 years, and now we know a huge amount about astronomy that comes from optical or electromagnetic signals. That only represents a small fraction of what's out in the universe. We've all heard of dark energy, dark matter. The actual electromagnetic energy is only about 4% of what's out there. So looking at the universe in a different way should, we believe, give us a lot, it already has in these black holes, give us insights that we wouldn't have had with just electromagnetic radiation. So far, we've had 5 years with a new kind of probe that relies on gravity instead of electromagnetic radiation. And we're starting to open up that new way to look at the universe. If you give us 400 years, like we've had in telescopes, I think we'll know a huge amount more about the sky than we do today. So with that, I'll end and thank you for your patience.
Thank you so much, Dr. Barish. This was an outstanding talk. I know that many people are putting in the chat, thanking you for that outstanding talk. I know that now we are doing like virtual applause because of the virtual world. But thank you so much for sharing such an amazing talk. As I mentioned at the beginning, we have several questions that the audience sent before the conference. Let's start with. So how neutrinos oscillations can be detected with LIGO? That was one of the questions that they sent.
Yeah, neutrino oscillations are, let me just say for the audience, neutrino oscillations are a really phenomenal physics feature that exists for one of our most exotic particles called the neutrino. We've learned that the neutrinos actually have mass, and they're not totally zero. That mass we don't know yet. It's really small. But it turns out that there's different kinds of neutrinos, just like there's different kinds of elementary particles. We have, for example, we have electrons, and we have something called muons. We have a heavier one. In fact, there's 3 families of particles that particle physicists look at, and therefore there's 3 kinds of neutrinos. It turns out that there's neutrinos associated with whether in the nuclear reaction there's electrons involved or there's muons involved. And those it could have all been 0 mass, but it turns out that neutrinos do have mass, and the different neutrinos have different masses. We don't know how much yet. And so they oscillate between themselves, which means they change identity over some period of time. We don't directly detect neutrinos in LIGO. We detect gravity, but we do look at our measurements at the same time that neutrino detectors. Well, the biggest one is at the South Pole, and there's one also in the Mediterranean. Look for neutrino oscillations. As we find sources that emit in the future, both neutrinos and gravitational waves, then we can bring the 2 sciences together. But our direct measurements in LIGO are just gravity. We don't detect the neutrinos.
Perfect. The next question that I have, does the discovery of gravitational wave prove that space-time is material?
Prove that space-time is material?
Yeah.
I don't know what the word material, what you mean exactly by the word material, but it certainly proved it. We knew pretty much that space-time has the features that Einstein has said because of other tests of it over time. But we don't know as of today that this formulation of space, so we know that space-time gets distorted, the general idea is right. But we don't know that Einstein's formulation is the right formulation. There are alternatives. And as we, and they will give different features of how space-time is distorted. And as we get better at making these measurements, we can distinguish whether Einstein's is the best theory or other theories are important. This is interesting in another sense. Something you read in the newspapers all the time is about dark energy and dark matter. Dark energy is particularly connected to the formulation of general relativity. And it could be that as we understand general relativity better or understand dark energy better, we'll understand what the right formulation is, because dark energy turns out to be a big mystery. The amount of energy in the universe, we don't know how to describe it, but it's most of what's out there.
Okay, perfect. Thank you so much. So I asked some of the panelists to start joining the conversation because I know they have some questions. So right after this question, I will let Mayra to ask her question. So the next question is, what has been your greatest challenge throughout your career and how have you overcome it?
Oh, I think the greatest challenge is one that we're all very used to, and that's basically the human challenge. You don't do physics at this scale without a large number of human beings being involved one way or the other. It's, I think, much more complex to deal with humans than it is to deal with technology. And so actually having a coherent and satisfactory way to do the science for everybody when you're working with a large group. In our case, we have 21 countries, and almost at the time we discovered gravitational waves, 1,000 authors on the list. So there's many people. You wonder why we need that many. It's because we have, fancy lasers, and we have state-of-the-art mirrors, and there's experts at all these things. Getting them to work together, dealing with the different cultures, the different human problems is by far the most interesting and the most challenging, I think. The technical ones, we learn how to do those.
Thank you so much for that answer. So I will let Dr. Mayra Lebron, who's a professor in the physics department at the University of Puerto Rico in Humacao, to ask her question.
Hi, Myra.
Hello, very nice talk. Very nice talk. I would like to ask you about the detection of gravitational wave using pulsars. I know that there are projects trying to detect gravitational wave with pulsar. Could you please tell us about that?
Okay. So if I understood the question, that it echoed a little bit, but I think you asked me about gravitational waves from pulsars. Is that? Yeah. Okay. So actually, if I go back in time 20 years and you had asked me what was the first thing we would detect with gravitational waves, I would have said pulsars. So I'll tell you my story. We haven't, but as of today, we haven't detected them, and I'll tell you why it's a challenge. So what's a pulsar for everybody that's still listening? A pulsar is a name we give to a spinning neutron star that emits radiation. So what happens is the star burns up all its fuel. I talked about it in my talk. It collapses, and depending on the size of the star, it may make what we call a neutron star. That's a very interesting object because it's a very compact nuclear object. So there's tremendous amount of nuclear physics that we aren't really able to probe otherwise. That is potentially understanding if we can study neutron stars. Neutron stars are often, I think maybe always, are the same thing as what we're calling pulsars. That is, they have in them electrons, for example. They spin, and that creates currents. And those currents give electric and magnetic fields and emission of light, actually. And so that light, like a what do you call it on the, to see where the ships are coming, spins around. When it points in your direction, you see it. So a pulsar means it basically gives light at whatever it is, some number of hertz, and it's telling you how fast it's spinning because it's sending that light. Now, nothing I said so far has anything to do with gravitational waves. But now I have a spinning object of a mass of something like a star for this discussion, going fast around, and it's made out of electrons, which are spinning around, and protons and so forth. And when they spin around, that means they make current. If they make a current around, that makes magnetic fields, and that's what makes the electromagnetic fields. And that's what the pulsar did. What about gravitational waves? To the extent that this spinning object is not a perfect cylinder, it will have little mountains on it. It'll have the asymmetries that give gravitational waves. And they don't have to be very big. The ones we've looked at so far, we have not seen gravitational waves. And if I translated that, a pulsar is about 20 kilometers across. We've seen to a level of about 1 millimeter that is perfectly spherical. The problem is the ones that we look at are the ones that are studied as pulsars. And the ones that are studied as pulsars are the oldest neutron stars that are out there. And by being old, they basically have become very symmetrical, and they give light and give electromagnetic radiation at a unique frequency, and that's monitored by the radio telescopes or whoever sees them, like Arecibo did. But basically, they have become so spherical in time that we don't see them. If instead we looked at a young neutron star that was made soon after the collapse of a star, then it's going to be more asymmetrical, and we can see them. The problem is, where do we look? If you look everywhere in the sky, or those if we don't know where they are, it's a computing problem that's well beyond anything we can do. So we can't really do that very well. We try. We even use background cycles from people's computers. You can join something called Einstein at Home and help us if you want. We'll borrow your background cycles, but we look for those. But we can't come close to what you could do if you had enough computing power. There just isn't enough to do that. So we're stuck by presently looking at objects that are pretty old, and they've developed enough spherical symmetry so we don't yet see the signal. Once we can see a signal, which I believe will be the next thing that we detect, still I'm optimistic. Once we do see a signal from pulsars or neutron stars, then it's a great laboratory, because once we see it, then we know one that's giving it. And we can study it as we make the detectors better. We can study it in detail. So once we're there, we have a laboratory that continues, not like the events that we're looking at now, which is just the merger of something, and then it's gone. So we look forward to detecting them. I'm still optimistic. I've told you why it's not really negative that we haven't seen them. It's a technical challenge because the ones that are known well are too spherically symmetrical, and they don't have mountains that are bigger than a millimeter, which is kind of where we are now.
Perfect. So, yep. Okay. So we have another question from the audience before we go to Andy's question. So Professor Josie Bedrine asked, can you talk briefly about the importance of having or have mentors in or during your journey?
Yeah, I think I survived without having really a good mentor. And so I understand what price you pay if you don't have a good mentor. As I said, I came from a background of neither parents going to college, certainly neither parents being anywhere close to science. They were ambitious for me, which was good. They thought I should be a doctor or a lawyer. So they had ambitions for me. They wanted me to go to college. So that they gave me, but they had no idea about science. I never happened to have a good mentor in school. The closest I came is something you mentioned at the very beginning. That was the tennis coach in our high school. So the tennis coach of the tennis team, we played other tennis teams, noticed that the other tennis players would always come to me with their school problems. You know, their problems in algebra or their problems in this and that. So he got the idea that maybe I was smart, and he would convince me that I had to not just go to college, but do something that was good. But he, of course, he didn't know anything about physics either. That's why I started as an engineering student. I love engineering, it's fine, but it's not really what I should have been doing even then. I was really lucky because, and so if I wasn't lucky, which you shouldn't have to be, and had a mentor, it wouldn't happen. For me, being an engineering student, I had to take a freshman course in chemistry and a freshman course in physics. It just so happened that that was the time in Berkeley when the same person who taught my freshman course in physics was discovering the antiproton, rather big discovery in physics. And that was pretty exciting. And I just decided that why would I do engineering and make, you know, build mundane things when I could understand something as crazy as an antiproton? So he became my advisor. He changed into physics, and everything was good from then on. But I think having a mentor is, you can do it the hard way like I did. But if you don't happen to come from a family that's highly educated that points you, then I think outside mentors, and usually the place for that is in school, is really important. So I think one obligation of school teachers, whether they're teachers that point people toward law or medicine, or science, or engineering, they play a really important role, because we all change. A very fair fraction of students change their mind when they're in college, but I think having some direction helps you do well in school when you're young, helps you have a direction. It's fine to change later, but I was floundering. I thought I was going to write novels or be a professional tennis player. I had no idea that I would be a scientist. So.
Awesome. Thank you so much for that answer. So we have a doctoral student from the Northern Arizona University. He's actually also an alumni from our institution, Andy Lopez Oquendo, and he would like to ask you a question as well.
Hi, Andy.
Hi, Barry. First of all, it's a pleasure of being here with you. And a couple things. First of all, I agree with you and Kevin. We should all play tennis someday together. And my question goes toward the LIGO sensitivity. It's just a matter of time, right, to discover this gravitational wave from binary neutron stars, from actually low mass, these neutron stars merging together. So can LIGO current sensitivity actually detect those small incidents in the universe?
Yeah, that's a good question. So let me reflect on it a little bit, how experimental physics work. So there's been two of the biggest discoveries in the last decade have been gravitational waves and something called the Higgs boson. The Higgs boson was absolutely of importance. We all learn E equals mc squared, but we never knew how energy creates mass. So energy creates mass through a process now we know called the Higgs mechanism, named after Peter Higgs, who proposed it 60, 70 years ago. So that's a very important discovery, that they saw the Higgs boson 5 years before we did at the big accelerator in Geneva, Switzerland. You haven't heard much since then about the Higgs boson. There's a little bit that's been learned, but not very much. Well, in our case, since we saw black holes merge, we now see neutron stars merge. We have hundreds of examples of black holes. I claim we'll see pulsars soon and so forth. So what's the difference? The difference, and this is often the case, it's nothing disparaging, but the difference is that when you collide particles together in a big collider like CERN, there's a lot that happens that's physics. And the Higgs boson is a little blip on top of that physics. That's why it took so hard and took a lot of work to do. But if you look at the paper that shows the Higgs boson, about at that exact mass, 98% of the signal is background, but it's physics background. You have to just know and study that background well enough to see a little 2% excess and attribute it to something else. The problem is, then what do? You found the needle in the haystack, but you can't throw away the haystack. It's there. So understanding the details of the needle is really difficult if you have a haystack. And that just happens to be the case. And so there, you have to do something else, like make a new accelerator that works in a different regime or something. And that's what they talk about. Our case, fortunate for us, is very different. We found the limit in us seeing gravitational waves was ourselves. How sensitive a detector could we make technically? Technical problems, not physics problems. How well could we isolate ourselves from the Earth? How good a laser could we have? How good is the vacuum? Those are all technical issues. So we've been able to progress quite quickly past where we made a detection. First, we couldn't make a detection for years. Then we detected them. Now we have 100 or so examples. Because of the fact that the background for us is technical, it's not physics. That means we can keep making better and better detectors until we run into something that's more fundamental. There are fundamental things. Eventually, we're not there yet. But there's fundamental background that you have to work around that are quantum effects in the mirrors themselves and in the process that you eventually will come to. Our limits now, as I showed here, come from really mundane technical things like the shaking of the Earth or the fact that we're working at room temperature. It's a big technical problem to work colder, but the KT noise that's basically limiting us now would go down substantially. The reason we don't do that is just we don't have the technology quite yet. You have to figure out what to make the mirrors out of, how to coat them, how to basically keep them cool without shaking them. And so they're just technical problems. They're doable. In fact, the Japanese at present are trying to make a cryogenic detector work. So you'll see this field advance, I think, for the next 10, 20 years, pretty well, probably another generation of detectors. I think eventually, like for telescopes or anything else, a new technique is going to have to be developed. It's clumsy to have to make these huge detectors to detect things. And it may be, for example, right now, the best idea, but we don't know how well it can be made to work yet. It needs a lot of work, is to make atomic interferometers. So the next step might be to make atomic interferometers. Anyway, this whole field is just unknown. We know we've opened the door, and we know we have a short-term 10 to 20 year or more future of just improving what we've got, brute force, if you want, cooling and so forth, technical problems. And that there's at least ideas like atomic interferometry to make a next generation and make a future kind of detectors. I think gravitational waves are here to stay, and it's just up to us to figure out how to make detectors that are sensitive enough so they're not so big and clumsy like LIGO. But this was a first try, a little bit brute force. I hope that's kind of what you wanted to hear.
Thank you so much.
Perfect. Thank you so much for that question. Also, Dr. Barish, for that answer. I want to be respectful for your time. I know you mentioned that you had to leave at 2:30 sharp, but I wanted to end with what advice would you give to the next generation, those students that were also maybe comment that were looking forward to work with the Arecibo Observatory, that I know that, as you told me before, you had some experience working here in Puerto Rico. What advice would you give to those students, the next generation?
You know, I think well, I have two things. One is don't be afraid to dream. Don't be afraid to try things. Life is short, and you should be adventurous. Don't take the easy way out. I think if there's another, so I think it's, you know, dreams are dreams, but some dreams can be made real. So you should be ambitious for what you really want to do with yourself and pursue it. I think there's also a lesson maybe in my career. I've done a lot of different things. I've done, well, I mean, forget about the student things, but I've done particle physics on particle accelerators. I've designed particle accelerators. I worked deep underground looking for magnetic monopoles. I've done this. So, and the people seem to, the problem is in our education system, we keep trying to make people who are really good. So we make them real experts at something. So you learn all the fields of physics as an undergraduate or astronomy. And then in graduate school, you narrow down and you only do solid condensed matter physics, or you only do high energy physics. And then you get narrower into a specialty in that. That is great to make you be able to contribute quickly, that you can get to a speed where you contribute. But I think it's a mistake for people to think that whenever their education ended, formal education ended, that's what they should pursue the rest of their lives. It's once you're trained as a scientist and you have some tools, you don't have to stop learning if some of the techniques might be a little different. You have all the tools to do science. And so don't be afraid to move in different directions and just pursuing the direction you were at in the beginning. So my first thing is dream and try to fulfill them. It's fine not to fulfill all your dreams. And secondly, be flexible and, you know, do what's most interesting at any given time. Don't feel you've been trained to go down a narrow road.
Perfect. Thank you so much. We really appreciate your advice, and hoping that you can join us in the future after we rebuild the Arecibo Observatory here in Puerto Rico as well.
Well, I hope to come back to your beautiful island and visit you in the finite future.
Yeah.
So,
thank you so much. It has been an honor and to host you here in Puerto Rico, especially at the University of Puerto Rico. Thank you so much for taking the time to talk to our community and for all the lessons and advice that you have provided to the students and to us. Thank you so much.
Thanks for your patience listening to me. And bye-bye.